Alright, so today we are going to solve some questions based upon the theory that we discussed in yesterday's class. Okay, so let us see this first question. A conducting sphere of radius r is given a charge q. The electric potential and the electric field at the center of the sphere respectively are. Can you tell me? Oh, we have not derived a formula for potential due to a sphere. You can guess that, right? We'll give some arguments about this formula afterwards. Okay. Oh, what has happened? But right now, see, you give some charge here. Okay, you give some charge here to the sphere, and we know that the electric field inside a hollow sphere is zero. So either it is option B or it is option D, right? So option D says both are zero, and option B says potential is Q divided by 4 pi epsilon naught R and the electric field is zero. So correct option is option B. Correct answer is option B. See how. So you give some charge here. Charge is capital Q and this is point at center. Okay. This is point O. So now what is the potential? We know potential due to a charge is 1 upon 4 pi epsilon naught Q upon R. Right. So if you consider small charge here, let's suppose that small charge is dq. So how much is potential at the center due to this small charge? So this point at the center is at distance capital R from the small charge. So due to this much charge only, due to this much charge, the potential is suppose dV and it's equal to 1 upon 4 pi epsilon naught multiplied by dq upon R, right? So now you take little charge here, potential due to that one will be equal to what? 1 upon 4 pi epsilon naught dq upon R, or you can call this one dq1. The other charge that you take, you can call it dq2. Then you take another charge. So you can perform this procedure over the total surface area of this sphere, right? So what will you get? So this is suppose dv1. Okay, you will get some dv2, dv3, so on and so forth. So total potential at the center will be equal to, you can say, integral of dv. Okay, it's integral of dv, which is integral of 1 upon 4 pi epsilon naught multiplied by dq upon r. R is constant, right? Okay, you can take all of this outside, so you get 1 upon 4 pi epsilon naught r integral of dq. So what is integral of dq over this sphere? It is just the total charge. It is just the total charge. Okay, it's capital Q, and that's why the formula becomes what? The formula due to, sorry, formula for potential due to a sphere, it is Q upon 4 pi epsilon naught R. Or you can just say, even if you don't think in terms of this integral, you can say, if you consider small charges, then this point is at the same distance from all those charges and potential is a scalar quantity. So the total potential at the center will be sum of potential due to all those small charges. So if you take small charges over the entire surface, okay, and find potential due to them, then since this point is at same distance from all those charges, okay, so you will have this thing common, 1 upon 4 pi epsilon naught multiplied by 1 upon r, or 1 upon 4 pi epsilon naught r will be common. Then what will be left? It will be dq1 plus dq2 plus dq3. If you consider all such charges on the surface, what will you get? You will get the total charge on the sphere. So this way or that way, actually it's the same thing. The answer comes out to be q divided by 4 pi epsilon naught r. Let us see next question. A bullet of mass 2 grams is having a charge 2 microcoulomb, through what potential difference must it be accelerated starting from rest to acquire a speed of 10 milliseconds? Sorry, meters per second, not milliseconds. Okay, so you have a bullet, it has some mass, and you want to accelerate it. So that bullet has got this much charge also, 2 microcoulombs. So what should be the potential? What should be the potential difference? Okay, so suppose the bullet moves from this point, let's call it A, to the point B, right? It has got some charge plus Q, and the potential difference between these 2 points is suppose VAB. Okay, potential difference between these 2 points is suppose VAB is the potential difference, or final point is B, so suppose it is VBA, right? Potential at final point minus potential at the initial point. Now we know that work done when a charge moves through some potential difference is equal to what? Charge multiplied by potential difference, right? Because how do we define the potential difference? So VBA it's equal to what? Work done to move that charge from I'm sorry, VBA is equal to work done to move the charge from A to B divided by the charge itself. Okay, and therefore work done will be equal to what? Q multiplied by VBA, right? So whatever is the work done, that much is the amount of energy that you are putting in this system. Okay, or you can say in this bullet. Okay, so the kinetic energy of bullet at this point B will be equal to what? The amount of potential energy it gains. Okay, so I can say kinetic energy is equal to, it is equal to what? WBA, and that is half of m into V square is equal to Q multiplied by VBA, and you want to find out potential difference. So move that charge on other side. So you get VBA, is equal to half of mv square, divided by Q, right? So then VBA is half of mv square upon Q. You have m, you have V, you have Q. Okay, so you can substitute all that and you can find out the potential difference. Okay, so it is half of 2 grams, which is 2 multiplied by 10 raised to minus 3 kilograms. Then V is 10 meters per second. So 10 square, and charge is 2 microcoulombs. So it is 2 multiplied by 10 raised to minus 6. So this 2 gets cancelled. 10 raised to 2 is 100. And if you take 10 raised to minus 6 in numerator, becomes 10 raised to plus 6. It is 10 raised to 6 minus 3, that's 3, plus 2. So 10 raised to 5, right? Divided by 2. Or you can say it is 10 times 10 raised to 4 divided by 2. Okay? That is 5 multiplied by 10 raised to 4. So options are 5 kilovolt, 50 kilovolt. It is 50 kilovolt, right? It is, you can write 50 multiplied by 10 raised to 3 volts. So it is 50 kilovolts. Option B. All right. Let's see next one. The electric potential at a point in free space due to charge capital Q coulomb is Q multiplied by 10 raised to 11 volts. The electric field at that point is. This is the question. So you have the formula for electric potential, right? Electric potential due to a charge V is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R. Okay, and this is given to be Q multiplied by 10 raised to 11 volts. What is the electric field? This question. So E is equal to, we know, 1 upon 4 pi epsilon naught multiplied by Q upon R square. Okay. So first of all, we have to find out R, right? We have to find out R. So V is given. So V is Q multiplied by 10 raised to 11. And we must remember the value of 1 upon 4 pi epsilon naught. It is 9 multiplied by 10 raised to 9, right? So then we have Q upon R. So this Q and Q gets cancelled out. Then we can move this 10 raised to 11 on this side, R on the other side, R on the other side. So I get R equals to 9 multiplied by 10 raised to minus 2, right? Because if you move 10 raised to 11 on other side, it becomes 10 raised to minus 11. Okay, so 10 raised to 9 minus 11 is minus 2. Okay, so R is 9 times 10 raised to minus 2. Okay, and then what would be the electric field? So the electric field, see, is 1 upon 4 pi epsilon naught multiplied by Q upon R square. Okay, so you already know what is 1 upon 4 pi epsilon naught Q divided by R. It is Q multiplied by 10 raised to 11. So this thing I can write 1 upon 4 pi epsilon naught multiplied by Q upon R multiplied by 1 upon R, and this thing is the electric potential. It is 9, sorry, not 9, Q multiplied by 10 raised to 11. Okay, so this is equal to I'm sorry, Q multiplied by 10 raised to 11, and in denominator you have R, which is 9 multiplied by 10 raised to minus 2. We can see, we know that 1 upon 4 pi epsilon naught is 9 multiplied by 10 raised to 9. Okay, so here we can adjust 9 multiplied by 10 raised to 9, and it will give us 4 pi epsilon naught in the numerator. Okay, so let's do that. So if we do that, what do we get? If we do that, what do we get? See, this 9 multiplied by 10 raised to 9. So I am dividing by 10 raised to 9. So I have to multiply by 10 raised to 9 2. And if I take this 10 raised to minus 2 to numerator, it becomes 10 raised to plus 2. Okay. So it is 10 raised to 13 already. Then again I have to multiply by 10 raised to 9. So what do I get? I get 10 raised to 20, 13 plus 9. Okay. So Q is there. Q is there. Okay. So I have adjusted 9 multiplied by 10 raised to 9. Looking at the options, right? Because something multiplied by pi epsilon naught is there in all of the options. So we know 1 upon 4 pi epsilon naught is 9 times 10 raised to 9. So what is 1 upon 9 multiplied by 10 raised to 9? It is 4 pi epsilon naught. Okay, so this thing is 1 upon 9 multiplied by 10 raised to 9 is 4 pi epsilon naught. So what do we get? The answer is 4 pi epsilon naught Q multiplied by 10 raised to 22. This is the electric field, volts per meter. So it is option C. Option C is the answer. Okay. Next question is, as per the diagram, so this is the diagram, a point charge Q plus Q is placed at origin O. So let's place charge plus Q at the origin. Work done in taking another point charge minus Q from a point A, this is point A, whose coordinates are 0A, to another point B, coordinates are A0 along the straight path AB is. Okay, so A0. Alright, so work done is it 0 or other options are there? So first of all, does the work done against the electrostatic force depend on the path? Does it depend on path? Does the work done against the electrostatic force depend on the path? Yes, no. No, because it's a conservative force. How do we know it's a conservative force? We found potential, okay, before knowing that it's a conservative force. So we had found it out when we studied gravity, okay, gravitation. The gravitational force is a conservative force. It is one, sorry, not 1 upon 4 pi epsilon naught. It's g multiplied by m1 m2 upon r square. Okay, so if we consider two bodies, masses are constant, g is universal gravitational constant, so this force is inversely proportional to r square. Okay, and it is directed along the line joining the two masses, right? Okay, if this is m1 and this is m2, so force due to m1 on m2 is along this line. Okay, same is the case with the electrostatic force. If you consider two charges q1 q2, the force is directed along this line, okay, towards, see, towards q1 or away from q1. It depends whether charges are like charges or unlike charges. And this force is also inversely proportional to r square. Okay, so now this is the similarity between gravitational force and the electrostatic force. So what is the similarity? Gravitational force is directed along the line joining the two masses. Electrostatic force is also directed along the line, okay, joining the two charges. And this one is inversely proportional to r square. This one is also inversely proportional to r square. So we had proved that, I mean, we had studied that this one is a conservative force, and I had explained it, giving some examples. Okay, finding out the work done along 2 3 paths. So if this one is conservative force, this one must be a conservative force. And work done for a conservative force does not depend on the path followed. Okay, work done for a conservative force does not depend on the path followed. Okay, and therefore we can define potential energy for bodies under the action of conservative force only. Okay, so this thing we had studied, and we have derived potential energy for the electrostatic force also. Okay, so work done does not depend on the path. So this thing along straight path AB, so they are saying work done in moving this charge capital Q minus Q from A to B. Okay, so whether you move it like this or like this, okay, it doesn't matter. Work done along all such paths will be equal. And how much would be that work done? How much would be that work done? It is equal to change in potential difference, right? Work done is equal to change in potential difference. So potential when that charge is at point B, okay, minus, or I can say work done is equal to potential difference multiplied by charge. So VB minus BA multiplied by the charge that you are moving. You are moving charge minus Q. So now question is, how much is VB? How much is potential at this point? So what is distance of this point from O? Okay, what is potential due to plus Q at this point? So how much is the distance? Distance is A, right? So potential there is 1 upon 4 pi epsilon naught multiplied by Q upon A. And what is potential at A? So potential here is also A, because the coordinates of this point are 0, A. So this much distance is A. Okay, so it is 1 upon 4 pi epsilon naught multiplied by Q upon A, right? Multiplied by minus Q. But since potential is same, potential is equal at this point and this point, so potential difference is 0. That means no work is done. Okay, so work done is equal to 0. Okay, so this question shouldn't take any time actually. Okay, this question should not take any time. So moment you see the coordinates, see the coordinate of this point at 0, A, that means it's okay, this has got only y coordinate. So this is at how much distance from this point? Distance A. Then Coordinates of this point are a0. So it is at distance a from this charge q. So this question shouldn't take any time. Okay, potential at this point and this point is equal because both the points are at same distance from this point. Okay, or this charge you can say. Since potential at those 2 points is zero, sorry, those points is equal, there will not be any work done to move a charge from this point to this point, right? Short electric dipole has a dipole moment of 16 multiplied by 10 raised to minus 9 coulomb meters. The electric potential due to the dipole at a point at distance of 0.6 meters from the center of dipole situated on line making an angle 60 degrees with the dipole axis is. So there is nothing in this question. Okay. So what do we have to do is we just have to find out potential due to dipole. So it's 1 upon 4 pi epsilon naught. Just write down the formula, substitute the values. P cos theta divided by r square. Okay. So this thing we must remember it is 9 multiplied by 10 raised to 9, 1 upon 4 pi epsilon naught. It is given in this question, but they may not give it because see, in this question, it was required, right? This is also a NEET question. This was required. Okay, putting that only, we got this answer. So it was not given. Okay, so sometimes they might give it, sometimes they might not give it. Okay, so if we remember this, it simplifies our calculations. So it is 9 times 10 raised to 9 and P is Q times 2A. So dipole moment, okay, dipole moment is directly given. It is 16 multiplied by 10 raised to minus 9. Okay, and angle is 60 degrees. So we have cos of 60 degrees divided by what? Distance is 0.6 meters. And you have square of that 0.6 square. Okay, so this can be written as 9 multiplied by 10 raised to this 9 and this minus 9. It gets cancelled out. I'm sorry. So it is 9 multiplied by 16 multiplied by cos of 60, which is 1 by 2, and in denominator you have 36 multiplied by 10 raised to minus 2. Okay, so let's check 36 multiplied by 10 raised to minus 2. Okay, so 9 fours are 36, 16 divided by, you have 16 divided by this 4 and this 2, that's 8. So it is 2 multiplied by 10 raised to 2. Yeah, it's option B, right? Okay, 200 volts is the answer. Anyways, let's move on to the next question. 4-point charges minus q, sorry, 4-point charges minus capital Q minus small q, 2q and 2q, 2 capital Q are placed one at each corner of the square. The relation between q and q for which the potential at the center of the square is 0 is. So this one is also simple. See, if you draw a square, so these are sorry. Okay, so these are 4 charges at the 4 corners of the square. Okay, and the charges are minus q, then minus q, 2q and 2q, and it's given that potential at the center is 0. So the center is at same distance from all these points, from all the 4 corners we can say. Okay, so what will be net potential? So net potential is given to be 0. So potential due to minus q, it will be just sum of potentials due to all the charges. So potential due to minus q, 1 upon 4 pi epsilon naught, we can say it is k multiplied by minus q divided by r, plus potential due to this minus q, okay, minus small q, is k multiplied by minus q upon r, plus you have 2 small q, k times 2 small q upon r, This is potential due to this charge. So K times 2Q upon R, and plus you have K times 2 capital Q divided by R. This is equal to 0. Okay, so if you notice, we can take K upon R common from all terms. So we can take it common and take it on other side, so it goes into the denominator, right? So 0 divided by anything is 0. Okay, so okay, we can move it on other side, right? I mean, we can divide by K upon R to this equation. So what will remain? Minus Q, then minus Q plus 2Q plus 2Q is equal to 0, or you can say minus Q plus 2Q is Q, right? 2Q minus Q is capital Q plus small q is equal to 0. So capital Q plus small q is equal to 0. So that implies that Q is equal to minus small q. Okay, so it's option A. Option A is the answer. Let's move on to the next question. So next question is, four electric charges plus q minus q minus q plus q plus q minus q minus q are placed at the corners of a square of side 2L. So side of the square is 2 times L. The electric potential at A, electric potential at this point, midway between two charges, capital Q, sorry, not capital Q, plus small q plus and plus q, is what will be the potential? This is the question. Okay, so let's calculate the potential. So how much would be potential due to this capital Q and capital Q? So potential due to capital Q is K multiplied by Q upon R, and okay, Q upon L, let's say L, because this side is 2L, so this much distance is L, right? And we have two such charges. We have two such charges. Okay, so it is K multiplied by Q upon L multiplied by 2, plus then we have potential due to these two charges. So for that we need to know this distance. Okay, we need to know this distance. So let's call this distance R. Okay, let's call this distance R. Then this is this much distance. Okay, from here to here it is 2L. This distance is L. So using Pythagoras theorem we can find out this distance, right? So R square is equal to 2L square, sorry, not 2L square, 2L whole square plus L square. Okay, so which is 4L square plus L square, that is 5L square. This is R square. So what is R? R is equal to root 5L. Okay, so then what will be potential due to these two? So it is 2 times K multiplied by minus Q upon R. Okay, so this will be total potential. So again we can take K common, we can take 2 common, so it is 2K multiplied by, and we can also take Q common. Okay, so let's take Q common. So 1 upon L minus 1 upon R. And what is R? It is root 5L. So we can substitute that. So what do we get? And in options it is 1 upon 4 pi epsilon naught. So it is 2Q divided by 4 pi epsilon naught, and it is 1 upon L minus 1 upon root 5L. So we can take L common too. Okay, so it is 1 minus 1 upon root 5. Option C, 3 charges each plus Q are placed at the corners of an isosceles triangle. Okay, ABC of sides BC and AC equal to 2A. So BC and AC, these are 2A. D and E are midpoints of BC and CA. Okay, D and D and E are midpoints of BC and CA, the work done in taking charge Q from D to E is. This is the question. Okay. So you have three charges. So this charge plus Q, and plus Q. And then you have another charge, capital Q, which you move from this point D to this point. So how much will be the work done? This is the question. Charges plus Q and minus Q are placed at points A and B respectively. Charges plus Q is kept here, minus Q is kept at point B, and A and B respectively, which are a distance 2L apart. The distance between these 2 points is 2L. C is the midpoint between A and B, so this much distance is L. Right, distance between B to C is L. The work done in moving charge plus Q along the semicircle, along this semicircle. So charge is here initially, to move it to the points, to the point D. Okay, CRD. So what will be the work done? Once again, we have to find out potential only. So, all right, let's do that. So how much is potential at D? We are moving this charge, so we have to neglect that potential due to other charges. Potential at D is equal to what? Due to this minus Q, it will be K times minus Q divided by distance L. Okay, because it is at distance L from minus Q. This is semicircle, so this distance will be equal to this distance, radius of the circle, radius of the semicircle. Then this much distance is 3L, right? This is 2L plus L, 3L. So potential due to plus Q is K multiplied by plus Q upon 3L. Okay. So therefore potential will be, it will be, let's make denominator same. So Q upon L we can take common. Okay. So it is KQ upon L multiplied by, this is minus 1 and this is 1 by 3. So minus 1 plus 1 by 3 is minus 2 by 3. Minus 2 by 3. Okay. And then what is VC? So VC is equal to, minus Q multiplied by, okay, it's at same distance from minus Q. Alright, so it is K multiplied by minus Q upon L plus, actually then we don't even need to solve this much. Okay, so this potential is common. So when we subtract, right, because how much would be work done? VD minus VC multiplied by charge Q, potential difference multiplied by charge. So when we subtract, this will get cancelled. Okay, plus we have potential due to the charge Q. So which is what? K into Q upon this much distance. So it is K multiplied by Q upon L. So this will get cancelled when we subtract. Okay, so it is K into Q upon 3L minus K into Q upon L. Okay, so K times Q upon 3L minus K times Q divided by L. This much is potential difference multiplied by, you have that charge, capital Q. Okay, so then again it's K times Q upon L, you can take common. So 1 by 3 minus 1 is minus 2 by 3. So how much would be the answer? It's equal to minus 2 by 3 K times Q upon L, and K is 1 upon 4 pi epsilon naught. So the answer is, work done is equal to minus 2 upon 4 times 3 is 12 pi epsilon naught multiplied by Q upon L. So yeah, 2 divided by 12 again. Okay, so it's 1 by 6. So minus q upon 6 pi epsilon naught L. This should be the answer. And that q is there, sorry. That q is in multiplication. Minus q times q upon 6 pi epsilon naught L. It's option C. So again, this is similar question, right? But there is only, yeah, there are three charges, q1, q2, q3. So two charges q1 and q2. Two charges q1 and q2 are placed 30 centimeter apart. So this question is kind of repeated, right? Yes, it is almost similar question. Two charges q1 and q2. These are q1 and q2 are placed 30 centimeter apart. So this much distance is 30 centimeters as shown in the figure. Third charge q3 is moved along the arc of a circle. Third charge q3 is moved along arc of a circle of radius 40 centimeter from C to D. The change in potential energy of the system is q3 divided by 4 pi epsilon naught k, where k is. This is the question. So see, okay, so you are moving this charge. That means you have to find out the potential due to remaining two charges. Okay, so you are moving this charge from C to D. So for these 2 points, which charge is at same distance? Charge q1 is at same distance. Okay, so I can say potential energy will be equal to what? Potential energy is equal to uh, change in potential energy. Okay, so delta U is equal to the work done when you move that charge. So it is equal to final potential energy U at point D minus U at point D minus U at point C. Or you can say potential due to other two charges at point D minus potential at C multiplied by charge Q3. Okay, and this is equal to, now since these 2 points are at same distance from Q1, so I can say potential due to Q1 VQ1 at D plus V due to Q2 at D. Okay, VQ2 at D. This is, okay, V at D is V due to Q1 plus V due to Q2 minus V due to Q1 plus V due to Q2 at point C. Okay, multiplied by charge Q3. Okay, and then see, potential due to q1 is same, so this one gets cancelled out. That's what I'm saying. When you are calculating, just don't consider it. Okay, so what is potential due to q2 at D? So this much distance is 40, this is 30, so this distance will be 10, right? 10 centimeters. So it is equal to q2 divided by 4 pi epsilon naught r, okay, which is 10 centimeters. So 10 multiplied by 10 raised to minus 2 minus potential due to Q2 at point C. Here we have to find out, right? So if we connect these 2 points, we'll get this equilateral triangle. Okay, so this is an equilateral triangle. Let's assume that this is an equilateral triangle. Okay, so this one will be what? 50, right? Because this side square is equal to this side square and this side square. So we know 3, 4, 5. Okay, we know an equilateral triangle, very common equilateral triangle. Two sides are 3 and 4. Then the hypotenuse is equal to what? 5. So this is 30 and 40. So its hypotenuse will be 50. So this is 50 centimeters, right? And if we don't know, we can calculate it. So this is 50 centimeters. So how much would be potential due to Q2? This Q2 divided by 4 pi epsilon naught divided by, Q2 divided by 4 pi epsilon naught, this distance, which is 50. So Q2 upon 4 pi epsilon naught multiplied by 50 multiplied by 10 raised to minus 2. Okay. So then you can take 1 upon 4 pi epsilon naught common and Q2 common. So this is equal to Q2 Q3 divided by 4 pi epsilon naught, and this is 1 upon 10 raised to minus 1, and this is 1 upon 50 times, you can say this is 5 multiplied by 10 raised to minus 1, and 10 raised to minus 1 you can take it into the numerator, okay, which becomes 10 raised to plus 1. So 10 minus 10 by 5, 2, okay, am I correct? So this is 10 raised to minus 1, in numerator 10 raised to plus 1, that's 10. So this one is 10 raised to 2, numerator, sorry, 10 raised to minus 2, in numerator it is 100, 100 divided by 50 is 2, right? So this is 10, this is 2. So 10 minus 2, okay, which is 8. So 8 times Q2 Q3 divided by 4 pi epsilon naught, and this is given, it is Q3 upon 4 pi epsilon naught K. So this is equal to Q3 upon 4 pi epsilon naught K. And what is value of K? This is asked. So Q3 upon 4 pi epsilon naught and Q3 upon 4 pi epsilon naught will get cancelled. Oh, I cancelled Q2 in haste. So K equals to 8Q2. Option C is the answer. Let's move on to the next question. Identical charges minus Q are placed at each corners of cube of side B. Then electrostatic potential energy of charge plus Q, which is placed at the center of cube, will be. Okay, so this is very simple. You have 4 charges of minus Q placed at 4 corners of the cube of side B. Sorry, this is not a square. Okay, so there are 6 charges. Okay, because this is a cube, there are 6 charges placed at the 6 corners of side B. Okay, sorry. So this is a cube having side B. This is a cube of side B, and there are not, okay, there are 8 corners to the cube, not 6. There are 6 faces, right? So there are charges at every corner, minus Q, minus Q, minus Q, minus Q at every corner. Okay. And question is, what will be the potential due to all of this, all of these at the potential energy if you keep charge plus Q at the center of the cube? So first of all, we have to find out the distance of this point, the center, from any one of these charges. And for that, what can we do? How much would be that distance? Can you say? See, you can connect, this line, okay, and you can draw a perpendicular from here, okay, and then I can connect this charge to this point, okay. So yeah, so how much would be this distance first of all? So if this distance is b, then uh, this distance is b, this distance is b, so this will be, using the Pythagoras theorem, this distance will be root 2b, right? Because b square plus b square equals to this side square. 2b square equal to this side square. I'm sorry. So this distance is root 2b. Okay, this distance is root 2b, and we want half of that. We want half of that. So it is root 2b divided by 2. So that is b upon root 2. Okay. So if this point is, let's call this point anything. This is a. This is, let's call it b. This is o. Okay. So ab is equal to b divided by root. Got it? Yes, no? Okay. And this length is equal to b. So this is the center. So how much would be distance of the center from any face? It will be b by 2. So distance OB is equal to b by 2, right? So now this distance, we want to find out this distance. Okay. So distance AO. So we can say AO square is equal to OB square plus AB square, and that is B square by 4 plus B square by 2. Okay, square root AB will be B square by 2. So then this is 2B square by 4. Okay, we can take 1 by 4 common. So this will be 3B square divided by 4. This is distance OA square. And that means how much is distance OA? It is root 3B divided by 2. Okay, if my calculation is correct, this is root 3B divided by 2. Yeah. And then we want to find out the potential. So see, this much would be the distance. This much, sorry, distance of distance of the center from all charges is root 3b upon 2. And therefore potential will be what? K times, I can say 8 multiplied by q divided by this distance AO, or you can call it R. Okay, which is K 8K, which is 1 upon 4 pi epsilon naught multiplied by 8q divided by this distance root 3b by 2. So this 2, okay, we can divide this 4 by 2. So it is 2 pi epsilon naught, and we have 8 in numerator. So it is 4q. Okay, yeah, I have to move on to the next page. So it is 2q divided by pi root 3 pi epsilon naught b. 2q divided by root 3 pi epsilon naught b. This is the potential due to all the charges at the center, and you want potential energy when you keep charge plus q at the center. So potential energy will be what? The total potential multiplied by this charge plus q. Okay, potential energy U is equal to V times B, V times Q. So U is equal to V times Q, which is 2 times Q square divided by root 3 pi epsilon naught B. So this is the answer. Oh no, sorry. This is negative charge, right? All these charges, all 8 charges are negative. This should be, there should be this minus sign. Okay, minus sign here. Okay, this is negative, this is also negative. Minus 2q square divided by root 3 pi epsilon naught b. This should be the answer. Okay, actually they have, okay, yeah. So is it option, no option like that? There is only root 3 here. So have I missed something? Oh, this is 4 divided by 2, so it will be 2, and minus 8 divided by 2, so it will be minus 4, right? Okay, so it is minus 4. Calculation mistake, sorry. Okay, so it's option C. Option C is the answer. Yes? Okay. So question is simple, just little bit lengthy. Okay. Let us see next question. In bringing an electron towards another electron, the electrostatic potential energy of the system, so becomes zero, increases, decreases, remains same. Tell me, when you bring two electrons close to each other, what will happen to the potential energy of the system? will decrease, increase, remain same, or it becomes zero? It will increase. Very simple. Because two electrons will repel each other, right? So in order to move them close, you have to force. You have to exert an external force. Okay. Opposite to the electrostatic force. That means you are doing some work. So potential energy increases. You are doing positive work. Okay. Potential potential energy increases. All right. Let's see next question. There is an electric field E in x direction. If the work done on moving charge 0.2 coulomb through distance of 2 meters along the line making an angle 60° with x-axis is 4 joules, then what is the value of E? This is the question. Okay, that is electric field E in x direction. This is E bar. And you are moving a charge by 2 meters. So let's suppose charge is here. Okay, so charge is moved from this point along the line making an angle 60 degrees. So you are moving the charge like this. Okay, whatever is the displacement, R is suppose displacement. So how much would be the work done against electric field? So this is displacement. So work is done against electric field which is along x-axis. This is theta. Okay, so this much is displacement in x direction, right? So work done against the electric field, work done will be equal to what? Minus of x times force due to this electric field. Okay, work done will be minus of x times force due to the electric field, not the electric field. Okay, it is force into displacement, so it is minus of x times q multiplied by E. Okay, charge is q, right? So then now, okay, so now we just have to substitute values. So x is equal to what? X is equal to r cos theta. So w is equal to minus of r cos theta times E. So E is equal to w divided by minus r cos theta. But I guess they are not concerned about the sign. So it is 4. Okay, I missed q here also. So w divided by minus qr cos theta. Okay, so work done is 4. 4 divided by minus q is what? 0.2. R is what? 2 meters. And cos of 60 is 1 by 2. Okay, this 2 gets cancelled. 4 divided by 0.2 is 4 divided by 0.2. 4 upon 2 is 2. So 4 divided by 0.2 is 20. So option B. Right? It's minus 20. But we are not concerned about sign. Only magnitude is 20 newtons per coulomb. Okay. Yeah, question is very simple, right? Okay. Let's see next question. So these were NEET questions. There was one JE question in between. A charged particle Q is shot with speed v towards another fixed charge particle capital Q. It approaches Q up to a closest distance small r and then returns. If Q were given speed 2v, then the closest distance of approach would be. See, there is a fixed charge, okay, and there is another charged particle to which you are giving some speed. So because of that speed, it will move closer to this charged particle, capital Q. But since capital Q is repelling it, it will slow down and it will stop at a certain distance. Okay. Now which thing will determine that distance between two charges? So this charge will keep on moving till the time its total kinetic energy gets converted to potential energy, right? Because in moving closer to each other, okay, in moving closer to this capital Q, it's doing some work. And where is that work coming from? Kinetic energy. Okay, so I can say that kinetic energy is equal to work done, or initial kinetic energy is equal to final potential energy, right? So Ke initial in first case is suppose Ke1, it's equal to V1, and in second case Ke2 is equal to V2. Okay, and what is V1? It's K times Q times small q divided by distance R1, which is R. Okay, and V2, that means V final, is K times Q into Q upon R2. This R2 is what we have to find out. So we can divide these two. So Ke1 upon Ke2. What is Ke1? So Ke1 upon Ke2, or yeah, Ke1 upon Ke2. We want to find out R2, right? So Ke1 upon Ke2 will give us what? KQQ and KQQ will get cancelled out. It's 1 upon R divided by 1 upon R2. Okay, 1 upon R divided by 1 upon R2, and divided by R2, 1 upon R2 is multiplied by its reciprocal, so which is R2. So then what is Ke1? Well, let's move this R also on other side. So R2 is equal to Ke1 is half of mv square, and Ke2 is half of m multiplied by 2v square. Okay, and we are moving this R on the other side, then m and m gets cancelled, half gets cancelled. It is v square divided by 2v square, 2v square, which is 4 times v square. So that v square gets cancelled. So it is 1/4 only, 1/4 of R. This is the answer. Okay, so R2 is equal to R upon 4. It's option D. Alright, next question. Two charges of equal magnitude small q are placed in air at distance 2a apart, and third charge minus 2q is placed at midpoint. The potential energy of the system is, okay, this is very simple, right? So two charges q and q, they are at distance 2a apart, and in between them you keep minus 2q. How much is potential energy? Potential energy of the system is equal to what? Work done in assembling these charges. So when you bring, suppose this charge, first there is no work done. Then you bring second charge. How much would be work done? Work done is k multiplied by q into q divided by distance between these two. How much is that? 2a. Plus, when you bring this charge, there will be some work done again. How much is work done? So there is some potential due to this charge at this point, some potential due to this charge at this point, and so it is k into q upon a multiplied by minus 2q. Okay, so it is work done against this charge, and work done against this charge would be equal actually, because this is at same distance. K multiplied by this charge upon a, this is the potential of this charge at this point, multiplied by the charge that we are bringing, minus 2q. Okay, so then it is k times q square upon 2a, plus here you have minus 2q square upon a and minus 2q square upon a. Okay, so k times minus 2q square. Okay, that is minus 2q square plus minus 2 times q square is minus 4 times q square. Okay, this is q square upon a, right? Then k times q square upon a we can take common. So this is equal to k times q square upon a, we can take common. Then it's half minus 4. So what is half minus 4? It's minus 3 halves. Okay, or minus 7 by 2. So minus 7 by 2, where is minus 7 by 2? Yeah, in option D. Right, if you write this k as 4 pi epsilon naught. Okay, so it is option D is the answer. Got it? So sometimes there might be a question like this one also. This is quite laborious, but it's easy question. Okay, then let's see next question. So will it be 0? All right. So don't jump to this conclusion that there is 0. Okay, there is 0 in the options, so answer would be 0. Most of the times it is 0. Sometimes it is not. All right. 3-point charges q minus 2q and minus 2q are placed at the vertices of an equilateral triangle of side A. The work done by some external force to increase their separation to 2a will be. All right. So we have three charges. We have three charges at the vertices of an equilateral triangle. So it is sorry, q minus 2q minus 2q. So suppose first you bring this q. Okay, so how much would be work done? 0. Then you bring this minus 2q. So work done will be what? How much is potential energy of this 3? It is q multiplied by minus, okay, so k times q multiplied by minus 2q upon distance between them is a or r, a, plus now when you bring this one, so there will be work done against this and against this. So it is k times q multiplied by minus 2q upon a, okay, and plus it will be k times minus 2q multiplied by minus 2q upon a. So minus 2q multiplied by minus 2q upon a. So which is equal to? Let's calculate. So it is k times q square upon a we can take common. Okay, k times q square upon a we can take common. So here we have minus 2, here we have minus 2, and here we have minus 2 times minus 2, which is 4, and actually it is 0. Okay, so initial potential energy is 0, right? So this is initial potential energy. Okay, I have written in black and red. Initial potential energy is 0. So now, how much would be final potential energy if separation between them is 2 times A? So see, now symmetry will tell us here, okay, what will be final potential energy? You just have to change A to 2A because again it will be an equilateral triangle, right? It will be an equilateral triangle. Separation between them, it is changed from A to 2A. So it will be an equilateral triangle. So in all these equations, in all these terms, we just have to make A, we have to change A to 2A. So even if we do that, what will happen? You can take 1 by 2 common. So it is 1 by 2 multiplied by 0. So that is 0 again. So initial potential energy is 0. Final potential energy is also 0. Even if you change the distance between them. So work done will be what? 0. Because potential difference is 0. Difference in potential energy is 0. So yeah, in this question indeed it is 0. Got it? Okay. So let's see next question. Which of the following is not true? For a point charge, electrostatic potential varies as 1 by r. This is true. Okay. For a dipole, the potential depends on position vector and dipole moment vector. This is also true. Okay, it depends on the position of point and dipole moment vector. Right, because we have formula potential due to a dipole V is equal to 1 upon 4 pi epsilon naught multiplied by P cos theta divided by r square. This is the formula. It depends on dipole moment, it depends on cos theta. So cos theta will give us what? Position vector of this point with respect to the dipole. Right, because okay, theta determines the position. Theta and r determine the position. Okay, so this is also true. The electric dipole potential varies as 1 by r at large distance. Okay, we'll see this. And for a point charge, the electrostatic field varies as 1 by r square. So this is also true. That means this is not true. Okay, if one option has to be not true, then it is option C. Okay, see, let us see what is this. What is the option C? Electric dipole potential varies as 1 by r at large distances. So let's suppose you have a dipole. What is dipole? Plus q minus q. Okay, and you are at very large distance. You are at very large distance. So this is suppose your dipole. If you are at very large distance from this dipole, okay, not this much distance, very large distance compared to the length of dipole. So I can say plus q and minus q are almost at the same distance from this point. Okay, don't don't take it literally this point. It's at very large distance. Point is at very large distance. So charge plus q and minus q they are almost at same distance from this point, from that very large distance at point at very large distance. Okay, so that means potential due to plus q and potential due to minus q at that point is equal. But potential due to one is positive, potential due to other is negative. So what will be the sum? So potential at that point would be 0. Okay, so potential due to a dipole at very large distance is equal to what? 0. Got it? So it does not vary as 1 by r at very large distance. Yes, no? Okay. Potential due to a dipole at very large distance is 0. Yeah. So it's not this thing. It doesn't vary as 1 by r. That's why which of these is not true? The option C is not. Okay. Oh, there is one. How many question? One more question. All right. So I will include this one in homework. Okay. Charge q is placed at the origin O of xy axis as shown. Okay. Here the work done in taking charge q from A to B. Oh, actually, okay. This is a simple question. Work done in moving a charge. This is plus q. Work done in moving charge capital Q from this point to this point is. So distance of this point is B. Distance of this point is A. Right. So work done is equal to change in potential multiplied by charge. So VB minus VA multiplied by charge. Okay, that is K multiplied by Q, okay, small q upon B minus K times small q upon A multiplied by Q. And then you can take everything else common. So K is 1 upon 4 pi epsilon naught. you have q times q upon 4 pi epsilon naught 1 by b minus 1 by a. This is the work done, right? So is there such an option? Yes. Okay. So denominator, if you make common, so this will be b times a or a times b. So this thing you have to multiply by a. This term you have to multiply by a. This term by b. It is a minus b divided by ab. Okay. So it is option A. It's option A, right?